So welcome back to the last session. The first talk in this session will be given by Eric Mugnier from the University of California, San Diego.
So hi everyone, I'm Eric, and today I'm going to present my work that I did with my collaborators at UC San Diego, Laurel, automating generation of Dafny assertion. So before talking about what we actually did, I want to talk about the problem. As we know, like the automation in Dafny is not like fully automated, it is partial automation, and let's talk about like what does it mean. So let's take an example. Here we have a function, parse decimal string, which takes a string, ideally with numbers. So here 123.456. And what we want to have is, as an output, 123 on one side and .456 on the other side. And so if we want to try to write a semi-formal specification, what we would have is like we want parse decimal string to return as a first element S1, and as a second element, the dot plus S2. And so now that we have this kind of semi-formal specification, let's try to prove it. And so a way to do this is, in general, we're going to have a sort of like helper lemma on which we're going to prove these kind of things on the output of parse decimal string. And so first, there's like some precondition. Here it's just about like the number. S1 is made of numbers. But the main thing that I want you to see is the first precondition, for example, saying that like the first value of the tuple is S1, and here the second value of the tuple is the dot plus S2. So we see basically our specification. We have a specification here. And so how do we prove this? Well, we use basic inductions where we're going to start with a base case, and then we're going to call recursively parse digits and dos on a slice of S1 to get termination. And so when we think about proving things in general, there's the first thing when I think about it in my head is like, is it correct? And the answer is in general, yes. And the second thing, does it verify? And sometimes it tends to be a sort of like difference between is it correct and does it verify? And does it verify, I mean like does Dafny tells you like it's okay? And well, in this case, as I said, it's correct. But it does not verify. And the error that you would get is a post-condition could not be proved on the else path. And so what do you add in this case if you're an experienced Dafny programmer? Well, you add an assertion. And this assertion here is just to help the SMT solver, and it tells that like basically S1 is made of the first element plus the slice that we use after to show termination. And so that's something that like assertion you're going to write kind of all the time, and it's going to take a bunch of like your life away when you're writing program in Dafny. So there's a question is like, can we automate it? And so let's start by a really simple automation. Is like, can we generate just single assertions? Just one assertion. Every time I have a problem, I try to generate one assertion that is going to solve my issue. And so right now, the trend is using LLMs, so let's try to use an LLM, and hopefully it will work because they're so great now. And so we're going to use some kind of naive LLM prompting, which tells, like, can you fix this proof by inserting one assertion? And so we try to do that on a benchmark that we'll talk about after. And here is the graph. What you see is the number of attempts on the x-axis. So like basically you try, retry until you get something good, and sometimes you never get something good. And then the success on the y-axis. And so the baseline is my naive prompting, which is basically just this prompt and giving the lemma to fix. And what we see is we don't even get 10% success rate by default. And if we try to be a bit smarter and we add the error message, well, we barely get 15%. And if we think about usability, getting 50% success rate when you try to generate an assertion automatically is not something that we want to use. So the question is, why does it fail? Like, what kind of things does it generate? If we take our previous example, and our naive prompting again, what kind of assertion? So one of the first assertion I will generate is, for example, it's restating the precondition at the beginning of a lemma. It does not help. The second thing is like it states thing about the element of S1 in the base case, where the base case already proved automatically. And the third one is states things about S2, which are not even true. So if we summarize some of the problems that we have is like, these assertions are not helpful, they're potentially incorrect, and they can be in the wrong location. So can we do better? And that's where we come. Laurel is basically a tool that generates assertion by leveraging large language models. And so how do we do that? Well, we try to answer two questions that you would ask yourself when we try to write an assertion. The first thing is like, where do I put this assertion in my program or in my lemma? And the second thing is what? So what kind of assertion does it need? Like, does it need to know about like this slicing that I showed before, or what kind of type of assertion? Because there's sort of kind of type of assertions. And so what we start from is first our lemma, the error message that we got, and then the code base in which our lemma is made. And we're going to say that like, so at the beginning, your code base is going to be completely empty, but at some point, you're going to arrive to the sort of point where you already have some lemma with some assertions that are already there. And so for the where, we're going to use the error message to basically try to find a location, which we call the placeholder, to find a location for this assertion and basically give this location to the LLM. For the what, we use a sort of like more interesting hypothesis, which is the missing assertion are likely to be similar to the assertion that you previously wrote in your code base. And by doing this, we can already extract a sort of like assertion that we think will be similar, and I'll explain how this similarity works. And then we give this both of this input, the first assertion that is similar and the location, to the LLM, and this is what gives made our project, Laurel, and we are able to successfully generate our assertion for S1. So now I'm going to dive deeper into the where and the what, and what we actually did inside. So the where, the assertion placeholder. So we have kind of like some rule on how to find this assertion placeholder based on the error message. So the first thing that we see when we read the error message is, first, well, the error message indicates us a faulty branch. So if there is a faulty branch in the error message, we're going to restrict automatically the location of the placeholder to this faulty branch. Pretty logical here. And that's something that a user would do too. The second thing is, well, here, for the sake of fun, I added a sort of like intermediate variable, S1 slice. But basically, it's to tell you that, like, in general, in this faulty branch, there are already like variables or assumptions. You want to basically be after that, so you can include them in your assertion. Basically, use what has already been done in your proof. So in this case, you need to be after that in the program. And the last thing is like, basically here it's saying us like, oh, there's a violation and this violation happened on a return path. So basically we want to be as close as possible to the violation. So like at the end, basically at the return path, the last thing they stated. And so when we do this, basically we kind of restricted the location to only one line. And so we place a placeholder here. So we saw the where. Now what about the what? Well, what we say is we have a lemma, it's missing an assertion, and what we're going to try to do is try to find similar lemmas because we're going to they're going to have similar assertions to the one that we're trying to generate. And so let's take these two lemmas that, like, if we take with a human eye, they kind of look similar, but the question is, how do we compare them programmatically? And so there are different methods in the related work. On one side, you have like text-based. That's really efficient, so neural embedding, TF-IDF, all these kind of things, but they don't have like a sort of like understanding of the code structure, and they're kind of sensitive to, for example, variable renaming. On the other side, there's like all of tree-based structures, so let's say like you parse your program already, and you're able to get the AST, and then you're going to do some kind of tree edit distance to see how far it is. And this is a bit more complex and a bit more involved, because tree edit distance has some kind of complexity, and also like getting the parser to work is a bit harder than just the text. And so the question is, can we kind of be in the middle? And yes, and that's what we do using a hierarchical distance, where we first start by the characters, so the text, and then we go one level upper with the tokens, and then we have this measure of similarity above, like with the lines, and we encompass all of this into a sort of like measure of proof similarity. And so if we try to apply this to these examples, we see these colors that like basically tells you which line are similar, and then we can compute a proof similarity from this. But what I want you to see here is that if we kind of do this technique here, what we will see is like we will see the kind of same structure with the if-else that are appearing here, which don't have like these S1 and S, which are a bit different. And I guess like some text base could like match them well, but like the main thing is like if the body of this if and else is big, like the text base might not actually work, where like in our case, you would actually extract the structure. So finally, how does it work? Like I told you, how does it work? I want to tell you how well does it work. So the baseline, we saw this, so I'll pass on this, but I'm going to talk about the assertion placeholder, the proof similarity, and finally a DafnyGym dataset on which we evaluated all of this. And so the thing about our DafnyGym dataset is it uses like 3 code bases that are like all in Daphne, of course. So the first one is the standard libraries, then there's CDR, which is not anymore in Daphne, but like is an example of like pretty involved Daphne proof, and Daphne VMC. And what I want you to remember about this is like basically what I call extracted assertion here are assertions that if you remove, the proof will instantly fail. So no brittleness, no kind of thing, like just instantly fail. You remove this line and it will not work. And one other important thing that I want you to remember is that these lemmas from which we extracted the assertions are in general decently big. They're at least more than 10 lines, although some like at least 10 lines, and like some of them are like even above that, and which means that like as we saw before, like the proof get more involved the more lines there is in your lemma. And so how well does the assertion placeholder work? So start from a baseline. We add a placeholder on top of the baseline, so basically we provide the placeholder. And what we see is a 2 times improvement over the baseline plus error. The other thing that we see is already on the first try, you get close to 25% of success rate, which means that basically running once is in general most likely enough. But still, we get less than 35% success rate, which again, in terms of usability, we're not there. And I'm talking only about single assertions. Now we add proof similarity. And so here I have 2 things. The first thing is like we take a random assertion from the same code base. And the second thing is we use a similarity, which I call dynamic placeholder. But we use a similarity metric to extract our assertion. And what we see first is example assertion from the same code base are beneficial. They will help an LLM to generate the good assertion. The second thing that we see is example assertion that are similar using a similarity matrix are better. Like we actually get a better performance. And finally, while using this technique, we're finally above like a sort of 50% success rate to generate this assertion, which kind of starts to be potentially useful, although like there's still a lot of work to be done. So in summary, Laurel is a tool that automatically generates assertions by leveraging LLM. We use 2 things, the assertion placeholder and lemma similarity, and we use this on the DafnyGym dataset. And from the first thing, we get 2 times improvement, and on top of this, when we add the similarity, there is 30% on top of this. Finally, I want to say that we released a dataset DafnyGym that is available, and it's a nice website with an image generated by LLM. And also, this will be appearing at Uppsala 2025, so feel free to check this when the full final version is out. And even more important and interesting for me is now that I like worked on the tool, I do the thing in the opposite order. I want to understand what users want and need. And so I've been trying to do a sort of user study on understanding like how does Daphne affect software engineering in general. And so I'm looking for people that like used Daphne in like decent sized project like or in industry to be interviewed. Yeah. So thank you, and I'll take any questions.
Thank you. If you can go to the slide with the table with the numbers of assertions, I guess there was like about 1,000 assertions for each one, or for the first 2, and only 50 are the ones where you say you remove it, the proof fails. So the others, you can remove them and the proof still passes, or?
So this is not exactly true. So there's one part of the answer that is boring, is the first way I extracted assertion was not great in terms of like program. So I was doing this using regular expression, and they were not catching all assertions. After that, I implemented this better, and I could identify more assertions. The other part of the answer is, yes, there's a lot of assertion that you could remove, and it wouldn't change anything, or it would maybe affect the speed at which the proof pass, either negatively or positively. So I think there's two. There's first, the extracted assertion could have been done better. The second thing is, yes, there's still a lot of cleanings to do in these assertions.
Thank you. And another question, if it's fine. I guess if you look at you have about 50% success rate at the end.
Mm-hmm.
Did you try to look and see what kind of assertions it gets and what kind of assertion it fails to get? And if you have some kind of intuition about some mental model about what it can do and what it cannot do?
So we tried, and I think there's like the easy answer, which is the longest the assertion is, the more difficult it will be. Then if it's a sort of like unique assertion, it's the first time it appears in the code base, you might get a success rate that is lower. But the maybe more interesting thing sometimes is that like, so LLMs are really good at understanding just by seeing the name of a lemma or something, what it does. And so sometimes they will try to like use in the assertion some kind of like function or things like this. And this function wouldn't exist, but would be really close to one that exists. And so if you had like some kind of like fixing there, because it's called hallucination. It's hallucinating that this function exists, which it doesn't. But if you would be able to repair this assertion by just changing 1 or 2 characters, you would actually get something correct. So hallucination is a problem.
Thanks.
Let's thank the speaker again.